we're going to get started with our lightning review of everything in 6034. We're going to go over all of the topics we covered this semester in less than an hour. So we'll start with rule-based systems. We covered rules way back at the beginning of the semester before quiz 1. And if you remember, we had rules that we labeled P0, P1, P2. These were if-then rules that could also have ors and ands and nots in them. So we might have something like, if X has ice cream, then X is happy. And then we also had a bunch of assertions, which were statements that we assumed to be true. And we labeled those A0, A1, and so on. So we might have an assertion, let's say, Aaron has ice cream. And then we might have another assertion, Kim has chocolate. So then we could draw some conclusions from this system. We had two methods for doing that. We had forward chaining and backward chaining. In forward chaining, we went in iterations and just tried to draw all the conclusions we could. So in each iteration, we had some rules that matched, at most one rule that fired, and we generated some new assertions. So in this case, in our first assertion, it looks like P0 matches the assertion A0, and maybe we have other rules, so maybe P2 also matches. We can fire P0 if it creates a new assertion. So in this case, it would create the new assertion, maybe A2, Aaron is happy. And we would keep doing this until we run out of new assertions that we can create. Then we had backward chaining, where we start with some hypothesis that we want to prove. So in backward chaining, we might start with a hypothesis, say Kim is happy. We want to find out whether Kim is happy. Then we would build a goal tree from that, and we would find rules that could possibly produce that hypothesis, or that assertion. So in this case, P0 can, if we have the assertion Kim has ice cream. But there might be other ways for Kim to be happy. So in this case, if we don't have a way to produce Kim has ice cream, then that would be false, but maybe there's some other way for Kim to be happy. So we could keep doing that until we prove or disprove the hypothesis. So then we went on to search. We looked at about 10 different types of search. We started with basic or blind search. We had British Museum, which just enumerates every possible path. So it's not very efficient, but if there is a path, it'll find it, and it'll also find the shortest path. And then we had depth-first search and breadth-first search. So none of these use heuristics or path length because they're blind, but they do still search through a search tree. So depth-first search would go down to the bottom of the search tree first, then try the next branch and continue across the search tree, whereas breadth-first search would go one layer at a time. So first it would search to the first layer, and then it would go to the next layer and keep doing that until it gets to the bottom, or until it finds a path. We saw that all of these search methods can be represented using an agenda. Depth-first search would add paths to the front of agenda, like a stack, whereas breadth-first search would add paths to the back of the agenda, more like a queue. So then we had heuristic searches. Heuristic searches, we had hill climbing. We had best first search. And we had beam search. So all of these use a heuristic, which is some estimate of distance to your goal. Hill climbing would just start from the current location and choose the best path from there. Best first would look through all possible paths and choose the best path out of all the possible ones, where best is defined as has the lowest heuristic estimate to the goal. And beam search was like best first, but instead of looking at all of the paths, it would only keep the best beam width worth of paths at each level of the search. So that would constrain the search space more. And then we had optimal searches. Optimal search, the main one we had was branch and bound. Branch and bound was like best first search in that it reorders all of the paths before choosing the next best path, but it uses the path length traveled so far instead of the heuristic estimate to the goal. So branch and bound by itself is guaranteed to find the shortest path to the goal, but we wanted to improve on that, so we tried adding a heuristic. We said that the heuristic will need to be admissible if we want to guarantee that we find the shortest path to the goal. And then we also tried adding an extended set. The extended set would mean that if we come across a node that we've already extended, we wouldn't extend it again, so that would limit the size of the search tree. And then we tried adding both of those together, and that gave us A-star search. We had a few different varieties of A-star search, but if we used a naive extended set, then we found that the heuristic must be consistent, which is a stronger condition than admissible, if we wanted to guarantee a shortest path. So then we went on to applications of these search methods. Two applications were games and constraint satisfaction, or constraint propagation. In games, the main algorithm we looked at was Minimax. So the idea here is we were performing an adversarial search where there were two players who had opposite goals, and we had to find a path that balanced their objectives. So we had a game tree to search through that had nodes representing states of the game. Each node had a static value associated with it, and the edges represent possible moves in the game. So if we labeled these something like 6-0, 3-4 backward, then we might have, say, Max playing first and Min playing second. And we would find the best path through this recursive algorithm where we go to the bottom of the game tree and we see at this place, Min would want to take move 3. Here, Min would want move 0. And at the top, Max would want move 3 instead of 0. So that would give us this Minimax path, which is the path of optimal moves that the path of moves that the players will make if they play optimally. We improved this using alpha-beta pruning. In alpha-beta, if we got to some point in the search tree and we knew that the options couldn't get any better, then we would prune off the branch and stop the search. So in this case, here we know that we know that if Max goes down the left branch, Max will get a score equal to 3. So at the top, Max is guaranteed to get a score of at least 3. But once we look at this 0, then we see that if Max goes down the right branch, then they're guaranteed to get a score of at most 0. So there's no reason for them to go down that branch. So we would prune off that side of the tree, and that way we wouldn't need to search this last node. So that saves us some work. We also used progressive deepening. Progressive deepening was a way of embedding this depth-first Minimax search into a breadth-first framework. Because one problem with Minimax is if you're searching through a ginormous tree, like if you're playing chess, then you might go down the whole left half of the tree and run out of time before you have time to search the rest of the tree. So this was an anytime algorithm where we would go first to the first level and get a somewhat good answer, then go to the next level and get a slightly better answer, and keep doing that until we ran out of time. We improved that even further using the reordering trick. In reordering, after we went to each level of progressive deepening, we reordered the nodes to maximize the chances of pruning in the next level so that we would get to prune off more branches of the tree and spend less time searching through it. So then we had constraint satisfaction. In constraint satisfaction, we had a graph with a bunch of variables. We called this a constraint graph. So we might have A, B, C, and D. There were some lines representing constraints between the variables. These might be different types of constraints, like we could have A must be equal to B, but A must not be equal to D, for example. And then each variable had a domain, which was a set of values that it could possibly take on. So maybe A can be 1, 2, or 3, but B can only be 1 or 2, D can be 1, 2, 3, and C can be 1, 2, 3, 4. Then we had 4 possible methods for solving this problem. The first one was just plain depth first search. We would try a combination of values. We wouldn't cross out anything from the domains. And if it works, we're good. If not, we'll just backtrack and try another combination. The second version was depth first search with forward checking, where we crossed out values from domains but didn't propagate through the domain. So in this case, we might start with assigning a value to A. So A has 3 possible values. It can be 1, 2, or 3. If we try assigning A equals 1, then we'll cross out values from its neighbors, and that tells us that B can't be 2 because B must be equal to A, and D can't be 1 because D can't be the same as A. So that limits our search space, and then when we get to the next level with B, B has only 1 possible value instead of 2, so it will probably end up doing less backtracking that way. Then our next method was, again, depth first search with forward checking. But this time we added on propagation through singleton domains. So that was where if we reduced a domain to size of 1, like we did here with B, then we would propagate through it. So in this case, we would use the fact that B can only be 1 to possibly eliminate values from its neighbor D. And then we had a stronger version of that, depth first search with forward checking and propagation through any reduced domains. So if we reduce a domain at all, whether to size 1 or a larger size, so in this case we reduce D but not to size 1, then we would propagate through it and use the fact that D can only be 2 and 3 to remove values from B and C's domains. And then finally we had a method for reducing the domains before we started the search, and we called that domain reduction before search. So domain reduction before search doesn't make any assignments. It just goes through and makes the domains smaller so that our search tree will be smaller and we'll have an easier time when we actually do the search. So that was all of the classical AI part of 603.4. Then we went into the machine learning section. So we started with k-nearest neighbors and identification trees. In k-nearest neighbors, we mostly worked with data on a 2-dimensional graph because it was easier to picture. So we might have something like some A points and then some B points and another point of class C. The general objective in all of these machine learning methods was to classify new unknown points given some training data, which were points with known features and classifications. So in this case, we would have 2 features, x1 and x2, and we're trying to classify new unknown points in this space. One thing we did is we drew 1 nearest neighbor boundaries. And we did that by first drawing perpendicular bisectors between all of the points of different classes. So if those are the lines between the points, the perpendicular bisectors would go something like this. And then that would divide up the space. So in this case, we have everything over here is classified as an A, everything in the middle region is classified as a B, and everything in the right is classified as C. We could also use different values of K. So for example, if we were trying to classify some point that was right there, then with K equals 1, we would classify it as a C because C is its 1 nearest neighbor. But if we use, say, K equals 3, then we would look at its 3 nearest neighbors, and we would classify it as a B because the majority of its 3 nearest, there are more B's in its 3 nearest neighbors than there are C's. So in addition to different values of k, we tried different distance metrics. This was Euclidean distance, but we also looked at Hamming distance, cosine distance for measuring angles, and Hamming distance. Did I say Hamming distance? Oh, Manhattan distance. There we go. Manhattan distance, which is sort of similar to Euclidean, but based on vertical and horizontal lines. Cosine distance for measuring angles, and Hamming distance, which we can use to compare things that aren't numeric, so symbolic quantities or symbolic feature values. So to determine the best value of k and the best distance metric, we used cross-validation. In cross-validation, we set aside some section of the training data to treat as test data. And then we trained, or in this case, chose parameters based on the rest of the data and then tested them with the data points we had set aside. So we could use that to find a good value of k and also to find a good distance metric. In doing that, we wanted to prevent both overfitting and underfitting. Overfitting is when we pay too much attention to the data and we treat noise points or outliers in the data as being significant, whereas underfitting is if we don't pay enough attention to the data. So if we happen to have 4 Bs in this data, and we say everything is a B because we have more Bs than everything else, that's underfitting. So those are both things we wanted to avoid. The cross-validation, overfitting, and underfitting apply to all the machine learning methods. So another machine learning method we looked at was identification trees. In identification trees, the goal was to construct some series of tests that we could use to classify unknown points. So we started with, in most cases, a table of data where we had the classification and a bunch of feature values. So this could be something like whether or not you're a vampire, and then a feature might be whether or not you eat garlic, whether or not you cast a shadow. The classification in this case might be plus or minus. You could also have a word for classification. It doesn't have to be binary. And then each feature would have some value. So maybe this one is yes and no. And then for each feature, we would look at a decision stump and compute the disorder. So in the case of the test x1, the decision stump would have 2 branches, yes and no. In the yes branch, we would have 2 pluses, and in the no branch, we would have a plus and 2 minuses. So then we could compute the disorder of this test. And we would get 2/5 times the disorder of the left branch plus 3/5 times the disorder of the right branch. The disorder when the points are all the same is 0, because there's no disorder there. And the disorder when it's 1/3, 2/3 we found was 0.9. So that's a pretty high disorder. And then this would give us some overall value for the disorder of this test, and we could compare that to the disorder of the other tests and use that to choose the test with the lowest disorder to construct a greedy disorder minimizing ID tree. So in this case, if this test has the lowest disorder, we would start with test x1. We would say if the answer is yes, then it's definitely a plus. If the answer is no, then we'll have to perform some other test. And we would continue adding tests to this tree until we either run out of good tests to use or we've classified the data as well as we want to. So that's ID trees. And then we looked at neural nets. We did a lot of different things with neural nets. Neural nets could draw pictures, they could create logic functions, but it was all built from this basic single neuron. Oftentimes we looked at a single neuron with 2 inputs, x and y, weights on the wires a and b, and then it would produce some output. In this case, the x gets multiplied by a, y gets multiplied by b, and they go into this summation and thresholding function. So it has some threshold t. And then the output will be either 1 or 0, depending on the values of all of these parameters. So it's 1 if ax plus by is greater than or equal to t, and it's 0 otherwise. And for backpropagation, we replaced the stair-step function with a sigmoid function to make it differentiable, and then the output would range smoothly between 0 and 1. So backpropagation was another thing we did. We found that this looks like an equation, so we could use that to graph a line. So if we have x and y, then this neural net might draw some line and shade one side of the line based on the greater than or equal to sign. And we could combine these together to form a more complicated picture. So we might have a neural net with two inputs, x and y, and a whole bunch of layers of neurons with different connections between them. And then we would get some output at the end. And we found that the first layer of the neural net, the input layer, draws lines. Each neuron in that layer draws a single line just like this and shades one side of it. So the input layer draws lines. And then the remaining layers perform some sort of logic functions to combine those line shadings to give us our overall output of 1 or 0. So we looked at a few different logic functions. We looked at and, or, and not. These are all Boolean logic functions. We found that each of those could be computed using a single neuron. So we could have one neuron computing an AND function. But then we also looked at a more complicated function, XOR, that would require 3 neurons. And that was because if you draw out the XOR graph with the inputs, you can't separate it using a single line, so we had to combine other logic functions to make the XOR function. And then we said we used backpropagation to train the neural net, and that was a way of automatically determining the ideal weights and thresholds. So there's neural nets. And then we had support vector machines. Support vector machines drew a single boundary in some space. This was a binary classifier, so there are only 2 classes of points. We might have something like some plus points and some minus points. We use the convex hull method to find the boundary by hand. So we imagine that we were stretching a rubber band around each group of points. And then we use that. We found the points in the 2 convex hulls that are closest to each other and took the perpendicular bisector of those to get the boundary. So in this case, it would be there. And then we define some points as the support vectors. So in this case, we would have these 2 pluses as a support vector and that minus. We had either 2 or 3 support vectors when we were in 2 dimensions. And then we had gutters, which are the dashed lines running through the support vectors. We classified points using the rule, the sign of w dotted with x plus b. And the important equation here was the equation for the boundary line, w dot x plus b equals 0. So on the left side of the boundary line, in this case, w dot x plus b would be positive, and on the right side it would be negative. Right on the gutters would be exactly plus or minus 1. And we use that in other equations to determine the parameters of the SVM. We also had the supportiveness values that we represented as alpha. So we said that the supportiveness for a non-support vector is 0 because it doesn't play any role in supporting the boundary. Whereas for a support vector, it'll always be a positive supportiveness because it's playing a positive role in determining the boundary. To make SVMs more powerful, we applied kernels. So we had the basic linear kernel that just draws a line like this. We also looked at a quadratic kernel and other polynomial kernels that could separate more complicated data like this. They could draw a parabola or draw an ellipse or a circle or hyperbolas. And then we had the radial basis kernel that could separate basically any data set as long as we didn't have a plus and minus point directly on top of each other with the same features. So then we get into the 2 topics that we just spent the past few weeks talking about. So these should look familiar. We had Bayesian inference, or Bayes nets in general. Bayes net had a bunch of variables with various relationships between them representing dependence probabilistically. So we might have something like this. And then the rule was a variable is conditionally independent of its non-descendants given its parents. So in this case, if we're given D's parent C, then D is independent of A and B because they're non-descendants. So we computed probabilities using this. So in this case, we could say something like the probability of D given C and B is equal to the probability of D given C. We use D separation to determine what things were independent. And then we use naive Bayes classification, which is another machine learning method. And then finally, we learned about AdaBoost, which is a specific implementation of boosting. And that was basically a way of taking a weighted vote of a bunch of weak classifiers to combine them together and make a stronger classifier. So that produced a strong overall classifier, h of x, which was equal to the sign of a bunch of weak classifiers where each one has a voting power alpha. And then we used the AdaBoost procedure, which goes in rounds, to find all of the best weak classifiers to put in here. And that would give us a strong classifier. So that is everything that we covered in 6034 at a high level. Of course, there was even more in lecture because there are the right now talks too. This is basically all of the core material. So you've learned how to do a lot of things this semester. You've learned how to cause a computer to reach logical conclusions. You learned how to perform an efficient search through any search space, like a map or something physical or non-physical. You learned how to win at an adversarial game without having to perform a computationally intractable search that could take billions of years. And we learned how to solve a problem with any number of variables and constraints, ranging from assigning people to times at a conference, to assigning functions to rooms in a house, or avoiding a dementor on a train. And then we learned about supervised machine learning, where we had 5 methods for doing that: nearest neighbors, ID trees, neural nets, SVMs, and naive Bayes. And supervised machine learning allows us to classify basically anything from vampires to trees to Brexiters and turkeys and chickens. And we did that just based on training data, which were points with objects or people with known features and classifications. And then finally, we learned about AdaBoost, which was a powerful method for combining all of these weaker classification methods together to reduce overfitting and create a stronger classifier. So that was everything that you learned. But if we take a step back, I think all of these concepts embody the principle of vanishing intelligence, where once you understand how something works, it no longer seems as magical because you know how it works. And this was especially true with things like AlphaGo or Deep Blue, which are game-playing programs that probably seem pretty impressive when you don't actually know how they work. But I think knowing about how something works and knowing how a machine thinks also gives you power over it. So you can use that power adversarially to trick the machine, like we saw in lecture with deep neural nets. But you can also use it to work collaboratively with the machine and to perform a task more efficiently by using the machine's strengths to your advantage. So I think in general, 6034 is about more than just learning all these specific algorithms. It's really about thinking about thinking. So even if you're not planning to go into AI or machine learning, you can still use all of the tools that you learned in this class to be able to program a computer to solve a specific problem, or even to think about how humans think about problems. So if you enjoyed this class, I'd love to hear about what your favorite parts were, either in person or over email or through subject evaluations. And if you do give us feedback on subject evaluations, we will read it. And every year we try to make 6034 even better than the previous year. So one last thing I want to say, you've been a great recitation. And I hope that the skills you've learned in this class will enable you to accomplish all of your goals.